already learned quite a bit about waves from our last chapter. In this chapter, we're going to specifically be talking about sound waves. So let's review a little bit what you've already learned about sound waves. Sound waves are longitudinal waves. And so as a longitudinal wave, what that means is that the wave is going to vibrate the particles of the medium that it passes through parallel to the direction the wave is going. So if the wave is traveling this direction, the particles are going to be vibrating in this direction, back and forth like this, as the wave passes through. Sound waves normally go through air, at least when we're listening to them, they normally go through air. Now they will pass through other things as well. In fact, you can kind of sense that vibration that sound waves cause if you've ever been in a room where there's a really loud music. Sometimes you can almost feel the floor vibrating, or it's like you can almost feel the walls vibrating. And so what is happening there is that the energy that is being carried by the sound waves is being transferred to the floor and to the walls and to everything around it. And so that's why you feel like you're vibrating or the surroundings are vibrating if you're in a room where there is really loud music. Sound is going to travel actually faster in solids and liquids than it does in a gas. And the reason for that is because how the molecules are packed together. We'll talk a little bit more about how molecules are packed when we get into the chemistry portion of our physical science course. But just to give you a little bit of background, if I look at how atoms and molecules are packed together in a solid, you can see in this really simple diagram here that the molecules are packed very tightly together. And in fact, they're packed so tightly together that they really can't do any more than vibrate against each other. When you have a liquid, the molecules are still very close together, but they're packed loosely enough that they can actually slide past each other and move around. When you get to a gas, there's a lot of space in between the molecules of a gas. And so as a sound wave travels through a solid, the particles that it's vibrating are all right smack next to each other, and they're relatively close together in a liquid. It's a lot harder for a sound wave to travel in a gas just because the molecules are so far apart. So a solid will actually transfer sound more effectively than a gas will. And so that's one thing that you will need to keep in mind, is that sound travels faster in a solid and in a liquid than it will in a gas. So this is the fastest, and then this is the slowest as far as the speed of sound goes. Also, if we're looking at gases, the temperature of the air is going to make a difference as to how quickly sound travels. The higher the temperature, the faster the molecules move. And so if these molecules are moving faster, there's more of a likelihood that they will bang into each other. And so as those molecules are moving faster, the sound can travel faster. Again, some of these concepts about the molecular motion we'll hit in a lot more detail when we get into the chemistry part. But for right now, what you need to be aware of is that the molecules are moving faster as the temperature goes higher. And so as the temperature goes higher, the sound will move faster as well. And so in this equation, this will tell us how to calculate what the speed of sound is depending on what the temperature is. Now, in this particular equation, and you will want to write this down because this one is not in your textbook, the temperature has to be in Celsius. You can't use Fahrenheit, so it has to be in Celsius. And if the temperature was 0, then the speed of sound would be 331.5 meters per second. But the higher it gets, we're going to take that number and we're going to multiply by 0.6 and then add it to this number to calculate the speed of sound at that particular temperature. So let's say that the temperature outside is 20 degrees Celsius. And let's figure out what the speed of sound would be at that particular temperature. So what I'll do is I'll take V equals 331.5 plus 0.6 times 20. Okay, now If you've studied order of operations already, you know that what that means is that the multiplication has to be done before you do the addition. So if you have just a standard calculator, if it's not a scientific calculator, if you have just a standard calculator, make sure that you type this piece in first, 0.6 times 20, and then add the 331.5. So if you've got your calculator, you might want to grab it real quick. Type in 0.6 times 20, and then add 331.5. And so you should get an answer of 343.5. And when you use this equation, the units are going to be in meters per second. Okay, so I would really encourage you to get your calculator. Make sure you get the same answer that I got, because if you do it in the wrong order, if you don't do the multiplication first, you won't come up with the right answer. Okay, so why would we want to know something like this? Well, something like this is very helpful, for example, in a thunderstorm. Let's say that you're having a thunderstorm outside, and the temperature for your thunderstorm is 15 degrees Celsius. Is the temperature during your thunderstorm. And then let's further say that you see the flash of lightning and then you start counting seconds. How many seconds is it till you hear the thunder? Well, let's say that it's 2 seconds until you hear the thunder. So if I know these two things, the temperature and how long it took me, or how long it took to hear the thunder after I saw the lightning flash, I can calculate how far away from me the lightning flash was. So the first thing I'll have to do is I'll have to calculate how fast the speed of sound is at 15 degrees Celsius. So I will use this equation again. So velocity equals 331.5 plus 0.6 times 15 degrees, okay? And so when I do that, again, do the multiplication first, 0.6 times 15, and then you're going to add 331.5 to that, and you should get an answer of 340.5 meters per second. Now I want you to just compare here real quick. At 20 degrees, we said it was 343. Now at 15 degrees, we said it was 340. So just like I had told you, sound travels faster when your temperature is higher. Okay, so now that I know the speed of sound at 15 degrees, now I can figure out how far away the actual lightning strike was. And I can do that using one of the equations that we learned about when we talked about kinematics earlier. We said that speed equals distance over time. And so if I use some algebra and rearrange this equation, and you may not know algebra yet, and that's okay, because I'm just going to give you the new equation, and so you just need to write that new equation down on your card so that you'll be able to use it on your test. So I'm going to rearrange this equation, and what that means then is that distance equals the speed times the time. So to solve these thunder and lightning problems, you want to make sure you have this equation written down, and you want to make sure you have this equation written down. Okay, so now how far away was the lightning? Well, I'm going to take the speed, which was 340.5 meters per second, and I'm going to multiply that times the time. And I said, well, it took you 2 seconds to hear the thunder after you saw the lightning flash. And so when I multiply 340.5 times 2, that will give me a distance of 681. The seconds will cancel out, 681 meters. Okay? I will be asking you to do several problems like this, so make sure that you understand the process. You're going to first figure out how fast the speed of sound is at that particular temperature, and then given this time period, how far away is your lightning strike from where you heard the thunder. So there is a general rule, and you may be aware of this already. If you're in a thunderstorm, you likely aren't going to want to pull your calculator out and actually go through all this, but you can get really, really close if you will do this. Approximately for every 1 second between the lightning and the thunder, sound is going to travel either 1/5 of a mile or it's going to travel about 1/3 of a kilometer. So if you're measuring in the metric system, for every 3 seconds you count, that means that the lightning is going to be 1 kilometer away. If you're measuring in miles, then for every 5 seconds you count, the lightning is 1 mile away. So it depends which unit of measurement you're using. Now, you can't do that on the test. You can't just use that approximation on the test. I'm going to want you to do it this way and calculate it out more precisely. But the next time you guys have a thunderstorm, you can use that simple rule of thumb and calculate it that way.